So hello and welcome in this new lecture series, and this will be on natural convection. So I am saying that this is a new lecture series, but you can consider it as a continuation of the already existing series of convection heat transfer. So I am starting this as a new series because I want to add something else in that series, and that is why I want to start this as a new series. Okay, so without any further delay, let us start. So this is our first lecture, and this is on what? Natural convection. Okay, so I think the pen width is too much, so let me just, okay, all the pen widths are set at 4. I apologize for the delay. Okay, so natural convection. I will start from the uh, very basic, but those who are starting this playlist, I assume that you have a good basic level of knowledge of fluid mechanics and basic convection heat transfer. That is, you know fluid mechanics at a basic level, right? And by basic level means I am talking about the undergraduate level, and also you know something about the convection, at least you have studied the forced convection. Okay, so uh, now if I talk about the natural convection thing, see here we have two words. We have convection. So as I have told that I assume that you know that what is convection. So this is a mode of heat transfer, right? And obviously we need a fluid, and here movement of the medium is required, right? And actually this is nothing but uh, advection, okay, plus conduction, right? So conduction of heat assisted by advection of fluid. Okay, so we generally say that we have only two types or two modes of heat transfer, and those are conduction and obviously the other type is uh, radiation. So so convection is nothing but conduction, and we have the flow of fluid with that. So we know that if we have a particular wall, right, and here the fluid is flowing, maybe this is a fluid molecule, this is another fluid molecule. So then the heat is actually being conducted uh, like this in this direction. So if this wall is hot, then the heat will be conducted in this direction, right? If the wall is hotter than the fluid, so then this molecule will become hot, and then it will move forward, and then in this place a new cold molecule will come, again it will be hot, again it will move forward. So see, so there is only conduction, and we have advection with that, so that is nothing but convection. Okay, now we have another word that is very interesting, and that is what? That is natural. So the first question is that we have something called as natural convection. So do we have something called as unnatural convection? Okay. So first of all, the opposite of natural convection is forced convection. Okay, the opposite of natural convection is forced convection. So forced convection is what we call as unnatural convection, right? So first of all we have to understand that forced convection is equivalent to the unnatural convection, right? Now what is so unnatural about forced convection? The unnatural thing is this force. Okay, so we are forcing the fluid to flow by the action of maybe a pump, obviously maybe a pump, or maybe by any kind of slope, not slope, maybe of pump. Okay, so we are forcing the fluid to flow. So external means to uh, make the fluid flow. Clear? So this can be obviously a pump. Okay, now that means in natural convection there will be no external means. Okay, no external means like a pump, but still the fluid flow will be there. So how can the fluid flow if I am not making it flow? Okay, so now let us see that. So my next question is that how the fluid is flowing without any external means. Clear? This is my next question. Now we have to see that if I am not applying any kind of external force, nothing, okay, I only have a temperature difference. So what do I have? I have temperature difference del T and gravity. So I have G, right? So these two things I have, and obviously I have the fluid. Okay, I have to make this fluid flow. Okay, how can I do that? Uh, so let us see that based on that how to apply this temperature gradient so that this fluid will flow. Okay, before that I will ask you that, so here to make the fluid flow a particular fluid element, so if I consider a tank like this, okay, sorry about that. So if I consider a tank like this and we have a fluid, okay, okay, so this fluid is having a density rho. Okay, now you tell me that if I have the only force as gravity, you can say that no, I have the pressure also. So then I can say that by the law of fluid statics, the gravity and pressure are correlated by only this law, that grad of P is minus rho into G. Okay. So now gravity is not making the fluid flow only. Okay. Because we can see that here the gravity is still acting in this direction, right? Okay, if this is the downwards direction, then gravity is still acting in this direction, but the fluid is at rest. So how can we make the fluid flow? So due to gravity, how can we create an unbalanced force on a particular fluid element like this? Okay, so this is an arbitrary fluid element. So my question is that with the help of gravity, how can we create an unbalanced force on this fluid element? So we can now, analogous to this, I can draw another picture, right? So if I just copy it and paste it, okay. So now I have the same situation, but now instead of this fluid chunk, I am having a solid object. Okay, I am having a solid object, and the solid object is having a density rho s that is less than the density of the fluid. Okay, this fluid is having a density rho f. So if that is the thing, then we can see that here obviously I will not derive it. You can just see that there will be an unbalanced force here, and that is nothing but my rho of fluid minus rho of s into volume of the solid into g, right? And this we say as our buoyancy force. Okay, so I will write F subscript B. Okay, so buoyancy force. So by some means, if we can change the density of this fluid chunk, maybe we are changing it to rho f dash. Okay, then we can make this fluid flow. If this rho f dash is larger than rho f, then it will flow downwards. If this rho f dash is smaller than rho f, it will go upward. So we have to create a density difference. Now how can we do that? Okay, so we have to create a density difference. So uh, force because of density difference. Okay, so this is the origin of natural convection. Okay, but there is again a catch. I will pose a particular question, that can you imagine a situation where the density difference is there but the fluid is at rest? Take some time, pause the video, take maybe a few seconds. Okay, and I think some of you have figured out the answer, and the answer is that if we have a tank like this, right, and we can have two fluids. Okay, so if this is the interface, so we can have two fluids. This is fluid 1, okay, and this is fluid 2. Okay, this is fluid 2. So this fluid is having density rho 1 and this fluid is having density rho 2. Clear? And the gravity is acting in this direction. So if this is the case and I am saying that my rho 1 is less than rho 2, then I can surely say, by I don't have to apply any mathematical logic, any physics, by my experience I can say that this will be a system at stable equilibrium. Clear? That means here I can see that there is a density gradient in this direction, uh, I mean positive density gradient, where this grad rho is more than 0 and the direction will be this, right? The direction will be this. So this is the direction of grad rho. The density is increasing in this direction. That means grad rho is present here, but still the fluid is not moving. So now consider a second situation. Okay, so I will just, sorry, I want to just change its color. Okay, now consider a second situation. This is the first situation. In the second situation, rho 2 is less than rho 1. Okay, so that means now the density gradient will be in the opposite direction, that will be something like this, grad rho. Okay, so now you can see that, okay, if that is the case, then obviously the lighter fluid will come up and the heavier fluid will go down. Okay, okay, so that will be the case obviously, but the thing is that you think very much practically and also intuitively, that if this fluid is very much densely packed, okay, if this fluid having density rho 1, obviously I am talking about this condition where this rho 2 is a lighter fluid. So if this fluid is very densely packed and the molecules will not come here because of the thermal fluctuations, that is an ideal case obviously. So there is nothing called a strict and hard interface, okay, like this, like this. So what actually happens, that here we have molecules of this yellow fluid and here we have molecules of this green fluid. So here uh, as we move from this point to this point, okay, so the density of the molecules of this fluid, that is the yellow fluid, will decrease and the density of the molecules of the green fluid will increase, and there will be a zone where the density of both of the fluid molecules will be almost equal. So that is how the interface is created. Macroscopically it seems like an interface, but microscopically it is not a sharp line. Okay, so I mean because of the thermal because of the thermal motion, obviously the molecules of the green fluid will come here and the molecules of the yellow fluid also will go there. Okay, so that is how the heavier fluid will sink down and the lighter fluid will come up. Okay, but if we have the ideal scenario case that we don't have uh, anything like that molecular thermal motion, or the molecules of both of the fluid are so closely packed that they cannot penetrate each other, I mean there is not enough space for that. Okay, then in that ideal case I think this will be the situation that even if rho 1 is larger than rho 2, the the fluids will be at equilibrium. Okay, now um the main funda is that my question is, that means even if you forget the second case, the second controversial case, that is the rho 1 is more than rho 2, that means we have at least one case, that is the case 1, that is the case 1 where despite having a density gradient we are not having any fluid motion. That means any kind of density gradient cannot start natural convection. Okay, so this statement is not correct, that force because of density difference. Okay, now let us see mathematically. So condition for a fluid to be in static equilibrium. Okay, static equilibrium. So we all know that the condition is what? Grad rho, sorry, grad P is equal to minus rho into F. Okay, where this F is equal to body force per unit mass. Okay. Okay. So if that is the case, now what we can do is we will take curl in both sides. Okay. So this f is a obviously a vector, and this grad p is also a vector. Now curl of a gradient of a scalar is by vector identity 0, and this one will be minus of, if I take the minus common, okay, grad rho cross f plus f, okay, f grad rho cross f. Okay, so now this will be plus rho into curl of f. Okay, so you can prove this either by your vector algebra or by the I mean index notation. I am not uh, doing that here. Now we are considering that our f is equal to g. Okay, so if f is equal to g, then what we will be having, and also I consider, okay, plus uh, homogeneous, or I should say uniform, okay, gravitational field. Uniform gravitational field, that means my g is not a function of either of x, y or z. Okay, that means my curl of f is equal to curl of g, and that will be 0. Okay, now if I put this conclusion in this equation, then I will be getting what? I will be getting 0 is equal to minus grad rho cross g, because f is equal to g. That means the condition for equilibrium in a homogeneous or uniform gravitational field is grad rho cross g has to be 0, right? So this directly means that if I have 4 situations where, okay, grad rho and g, so okay, so I will just show you very clearly, that is angle between grad rho and g. Okay, so and the visualization and uh, equilibrium, yes or no, equilibrium, yes or no. Okay, so angle between grad rho and g is 90. First I am considering 90. Okay, so now visualization can be something like this. So if I take this kind of a color, so okay, so that means my g will always be in downward direction. Okay, and if I measure the angle from g towards grad rho, then my grad rho is in this direction. And what is my grad rho cross g? Is it 0? This is not 0. That means this is my grad rho direction. Okay, so grad rho is in this direction. That means maybe in this direction my density is changing. Rho 1, rho 2, rho 3. This is changing along this direction. And my g is acting along this direction. So yes, equilibrium will not be there. Okay, now it is 180. Okay, so if I just copy it, okay, and paste it here, what happened? Okay, So now it is 180, that means now my grad rho will be in this direction. Okay, so this is the direction of grad rho. So actually I should draw it with a different color, or maybe I will just change it. Okay, sorry about that. Maybe this color. Okay, this also I will change. Okay, now here we can see that my grad rho cross G will be 0. That means yes, equilibrium will be there. So it is yes, and this is no. Okay, the third condition is 270. Okay, and I can always paste it here. Okay, so according to the third condition, the grad rho will be in this direction. Okay, but again we can see that the grad rho cross G is not equal to 0. That means it will not be in equilibrium. And if I take 0 degree, so if again I paste the same thing, okay, so now my grad rho will be in the same direction with G, because the angle between them is 0. So then yes, the equilibrium will be there. So you see, this is the first case where the grad rho is in this direction. So this case, here the grad rho is in this direction. So if I have two fluids, rho 1 and rho 2, that means rho 2 is larger than rho 1. So that is the first case. And you see that this is the second case, right? Where if again this is rho 1 and rho 2, two fluids, then rho 1 is larger than rho 2. Okay, so this is the second case. So in both of these cases we see that the mathematics is saying that yes, we are having equilibrium, no motion. So in these two cases we are having the density difference, the density gradient, but there is no motion. But in these cases, we are having motions. Okay, now the funda is that the thing will be governed by this thing. Sorry, I mean whether there will be motion or not, that will be governed by this thing, or I should write in other words that it will be governed by the angle between grad rho and G. So we can see that if this is say theta, so if theta is a multiple of maybe n pi, okay, n can be the 0, 1, 2, 3, anything, then there will be equilibrium. So then there will be equilibrium. Okay, and if it is anything other than n pi, then obviously there will not be equilibrium. Clear? So that means you cannot say that if I have density difference, then I will have natural convection. No, you have to have the density difference such that the body force that will affect that density difference will be at an angle other than n pi. Okay, so that is the thing. Okay, so just for the sake of completeness, if this is theta and it is not equal to n pi, okay, then I can have another pair of image where this is your, okay, maybe this is your grad rho, any angle it can be. Obviously the equilibrium will not be there and the motion will be there. Okay, so this was a very subtle concept. Okay, and I think a very interesting one also. Clear? So now I will directly ask you that in your daily life you experience natural convection every day. Okay. And by the word experience means that you don't see or feel it, but it is happening every now and then maybe. So those of you who are tea lovers, you have your cup of teas, right? And I think obviously that you are served the tea, okay, hot, okay. So maybe it is having 70 degrees Celsius, but the outside is at 30 degrees Celsius. So obviously, from this wall of the teacup, this air will be heated up, and you see that air molecules at these zones, okay, at 30 degree, at at this zone maybe at 35, at this zone maybe at 50, at this zone 60, and at the adjacent it is 70. That means the temperature is changing, and we know that because of the change in temperature we can have a change in density. Okay, that means we have a change in density in this direction, and we already have our body force in this direction as g. That means we can have natural convection, okay, like that. So I will take this situation only, but now the cup walls will be vertical. Okay. So my first case will be nothing but, okay, natural convection, natural convection, okay, for a vertical flat plate. Okay. So isothermal case. The plate is having a temperature that is constant throughout the plate throughout the time. Okay. Okay. So now here I will obviously consider those conditions, that is for the fluid, it is a fluid having constant properties other than density. Okay, other than density. Okay, so let me not right now specify this condition. Okay, but I am saying that the flow is incompressible. Flow is incompressible. Okay, incompressible. So that means nothing but that my divergence of v is 0, and that is the um, I mean the continuity equation for a for an incompressible flow. Okay. See, I have not said that the fluid is incompressible. So there is a common misconception that incompressible fluid means incompressible flow, or the vice versa is true. No, incompressible flow is completely a kinematic condition, and it is saying that the volumetric strain rate will be 0, although the fluid can be compressible. Okay. On the other hand, an incompressible fluid, okay, can show um, compressible flow, okay, because of change in temperature. Okay. So now let us see, this is the only thing that I have mentioned as my assumption. Further assumptions I will tell subsequently. Now let me draw the schematic. So this is the hot plate. Okay, hot plate. So obviously if I have a hot plate, then the fluid then the fluid will rise through this and this side also, but the situation will be symmetric in both the sides. Okay, that is why I will be considering only one side. Okay, so I will be considering only the uh, only this side, that is the uh, uh, this one, left side. Okay, so now this is my coordinate axis y, and this is x. Okay, and this is the origin. Clear? So now this plate is having the temperature as T infinity, sorry, T, T maybe Ts, that is the T surface, and T infinity is the ambient temperature. Okay, and this Ts is larger than T infinity, greater than T infinity. Any other thing? Okay, obviously G is acting in the negative x direction, so this is the G, and this G is Gx minus Ex. So Ex is the unit vector in the positive x direction. So this is the Ex vector, and similarly this is Ey vector. If you want, you can write this as your Gx I cap, sorry, minus I cap. Okay, and here we have the fluid. Okay, here we have the fluid like this. Okay, so that means obviously that because of the change in the temperature, the density will change. Now let us see that first, that how the density will change. Okay, so for a for a simple compressible substance, simple compressible pure substance. Okay, my density I can write by the state postulate as a function of P and V. Clear? So sorry, P, okay, yes, P and V or P and T temperature. So obviously you can write in any other, in you can write as a function of any two other properties like H, V, like H, S, anything you can write. But here I want P and T only. Okay, so that means, okay, now if I have my reference temperature, okay, so rho r is my reference temperature. Okay, and we will see that generally we take it as rho infinity, that is rho at T infinity, that is density of the fluid at ambient temperature. Okay, so my difference between these two, or if I now write the Taylor series expansion, Taylor series expansion with respect to rho r. Okay, so Taylor series expansion of rho with respect to rho r. Now why I am writing this? Because I am interested that you just go back to that situation. Okay, so I will not just scroll up, but I will just draw here. You just go back to this situation, that if I have a fluid here, and if I have a fluid chunk like this, okay, then if I can change the density of this fluid chunk with respect to with respect to the density of the surrounding fluid, this is very important, that if I can change the density of this fluid chunk with respect to the density of the surrounding fluid, then I can have the motion of this fluid chunk. Okay, that is why I need to search, or I need to look for the change in density rho with respect to this rho r. And this rho r, we, as I have told earlier, that we take it as rho infinity. Clear? Now let us see that if I write the Taylor series expansion, rho is equal to rho r plus what? Del rho del, okay, so rho is a, extremely sorry, so rho is a function of t and p. So del rho, array, I don't know that what is happening. Okay, so del rho del t. Okay, so let me just, there has been a small l created. Okay, so del rho del t at constant p into delta t. Okay, so plus, and this is at tr comma pr. I mean, this del rho del t at constant p is calculated at tr comma pr, and plus del rho del p at constant t at obviously tr comma pr into delta p plus higher order terms. Okay, I think I got a mail. Okay, neglect it. So now what I will do is, I will take this rho r common. So I will get 1 plus 1 by rho r del rho del t at constant pressure at tr comma pr into delta t plus 1 by rho r, okay, del rho del p at constant temperature tr comma pr into delta p plus higher order terms, okay, plus 1 by rho r into higher order terms. Clear? Okay. Now first of all, what is this? This 1 by rho r del rho del t, okay, at constant p tr pr. What is this? So to make this term more familiar to you, what I will do is, I will write rho as 1 by v, that is my specific volume. Okay, so this will be Vr, okay, into del t of 1 by Vr. So minus Vr square into del V del t, okay, at constant P at Tr comma Pr. Okay, I think I have done it correctly, and this is minus 1 by Vr del V del t at constant P tr comma pr, and this is, we all know that only this part, okay, this part is, so I am writing minus and with the blue ink, this part is the coefficient of volumetric expansivity, okay, or we just loosely call it thermal expansivity, that's all. Okay, so, and I will term it as beta, and beta r, okay, because it is calculated at, so this is nothing but that beta at tr. Okay, now what is the second term? Second term means this term, let us see. So the second term is 1 by rho r del rho del p at constant t tr comma pr, right. Now again, if I do the same exercise, I will have minus 1 by Vr del V del P constant T Tr comma Pr. Clear? Okay. Now what is this? This is nothing but the isothermal compressibility. Okay. But now in this time, I mean here the minus will not be, I mean, I will not write like this, that minus of kappa. Okay, so isothermal compressibility I denote it as my kappa, and because it is isothermal I will give a superscript T, and it is calculated at the I mean state R, that is the reference state. Okay, so now for okay, for ideal gas, okay, if we consider a simple compressible pure substance, obviously that we are considering, now at a very high temperature and low pressure, if we can consider it as an ideal gas, okay, then for isothermal case, okay, so then for the isothermal case we have this equation Pv equal to constant, and for the adiabatic case or isentropic case we have this equation, right? Okay, so what I want to do is I want to establish a I mean I want to establish a correlation between this part and K. Okay, so K S T, that is the isentropic compressibility. Okay, and if we just go through this equation, so what you have to do is from this you have to find, I mean you have to find del V del T at constant temperature, and from this you have to find del V del T at constant entropy. Okay, so I can do it very quickly for you. So here let us see, if I just do it, so P dV plus V dP is 0. Okay, so that means my dV dP, okay, this is at obviously constant temperature, and that will be equal to what, minus V by P. And if I talk about this case, this will be what, this will be, okay, there was an alarm. Okay, I think I can only continue this for 15 minutes more. So this will be what, this will be P, okay, gamma into V to the power gamma minus 1, okay, into dV, okay, plus V to the power gamma into dP is equal to 0. That means I will have this as, okay, this as at constant entropy I will have, so minus V to the power gamma by P this one. Okay, so what I will have, minus V by P into 1 by gamma. See, if you put if you do this, then so now I will have that my K at constant S by my K at constant what, K, sorry, extremely sorry, K at constant S here, and R, that is the reference temperature, it is T here. Okay, so I want to compare this with K at constant S and computed at the state R. Okay, so this will be what, So this 1 by Vr thing will be cancelled out, and KRS means, okay, so minus V by P into 1 by gamma, and here it will be minus V by P, everything will be cancelled out, only 1 by gamma. Okay, that means from this I can write that my Kr at isothermal condition is equal to gamma into, okay, KRS. ये मतलब ये जो स्पेशल वाला K है ना, ये एक्चुअली K नहीं है, दिस इज कॉल्ड काप्पा. ओके, तो जो भी हो, आई मीन इट्स एक्चुअली हार्ड टू I mean write the same shape every now and then. I mean you can see this shape, this is, I mean, nothing. Okay, okay, so these Greek letters, I don't know that how, I mean, a person can write. So have you heard about the letter xi? So it is, so something like this, or maybe jo bhi ho. So okay, so now we can see that this is the isentropic compressibility, and this is nothing but we can write as this into minus 1 by Vr into del V del P at constant entropy, okay, at constant entropy, and computed as Tr comma Pr. Okay, and we can actually write this as, so let us just complete it, this part. So again minus this, okay, now 1 by Vr is equal to rho r. Okay, so this is equal to actually 1 by c square. Okay, because we know that I mean del P del V at constant entropy is equal to c square, where the c is the speed of sound. Okay, this can be easily proved by taking a control volume, okay, where we have that the speed of, I mean, maybe a vibrational wave or a disturbance wave is traveling. Okay, so if this is a front, okay, and it is traveling with c, okay, this is c and this is c plus dc, so we have to just balance the momentum and all the things. Okay, by this we can have this correlation. Okay, so if you have studied the compressible flow, then you can, I mean, correlate this, that how this comes. Okay, in compressible flow, just by balancing the momentum for I mean across a disturbance wave. Like if this is a medium, okay, if this is the medium and this is the disturbance wave, and maybe this is traveling with a velocity c. Okay, so in these two sides of this medium, okay, the I mean the velocities will be different. So what you can do is, you can do a, I mean, you can do an analysis like this, that you uh, the, uh, that you have to fix this one, and this medium is traveling like this. So here the medium is having c, and here after going through the disturbance it is c minus dc. Okay, here it is rho, it is rho minus d rho. If this is the case, then here it will be p, and it will be p minus dp, the pressure. Okay, so you have to do a momentum balance to get this thing. Okay, so जो भी हो, this is not the uh, I mean, this is not the thing for today's session, so I will not derive that. So now this will be minus gamma rho r by c square. Now, as I am just considering the ideal gas, so this will be rho means what? P by RT. right? So this will be okay. So uh, okay, so this will be P r by r into T r and c square. Okay, c square. So am I doing the right thing? Okay, I think I am doing the right thing. Okay, so now let us see that okay, so at this point what we can do is okay, so uh, just let us now go to this equation and I will just copy it. Okay, so now I take one assumption that my delta t and my delta p are small. Okay, that is the deviation from the reference state is small. Okay, that means my rho I can actually because of this I can neglect this higher order term, so this is almost 0. Okay, so this is I can say rho r 1 plus okay, so this is beta r delta t clear plus okay, now this will be what this we have seen this is minus gamma p. I think I am doing the right things. Okay, minus gamma p okay r by r trc square okay into delta p. Okay, so this is the thing. So now I have to actually go. I will give you the hint that you have to find the condition for from these terms in terms of two numbers. One is Mach number and another is Eckert number, and this Eckert number is actually correlated with this Mach number. Okay, you have to find this condition. I mean, if you don't know that what is Eckert number, it is v square by 2 cp into t, or you can see that v square by cp into t. Okay, so you have to find the condition in terms of Eckert number, that what is the I mean how the Eckert number should be. Should it be very small or large so that I can neglect this term? That you have to find. This is uh, this is your task, and obviously we will start from this point in the next lecture. Okay, so until that, goodbye, take care, and thank you.